which is the second module. And I will start to decompose the machine learning literature according to different data types and according to different tasks. All right, so first, data. So the majority of those machine learning libraries, for example, scikit-learn, what you just take a look, there's this data. We have the image loaded, but we have to reshape it into data. The reason is scikit-learn, their presumed data input type are something called tabular, or the form has this kind of matrix form. And we can think about like the features, different feature variables are different columns, they are aligned. And this is the first feature, second feature. So this is the feature direction. It can maybe represent the first pixel of that image, and then the x2 is the second pixel of that image, and until in the end, all the pixels in that image. And this S1 per row representing different samples. So this tabular data in the end is a matrix. So this part is the one we just showed is X, and this part is the Y. And we can just put this X train or Y train. You just actually took a look, right? You see this X train and Y train part feed into that classifier, and that's exactly look like this. In fact, matrix form, number of samples as vertical, and number of features as the columns, and then a separate matrix is about Y. But they're totally aligned, indexed the same as the X train. So this is called tabular data. All right. So there are different kind of types of, especially the last Y, that Y portion. So it can be real numbers. It also can be symbolic, more like a binary that we already had, like in the previous examples, +1, -1. So for example, so the Y, I'm going to talk about it in the later. So what can be the X? So very classic example, because I told you guys I'm going to use COVID or biomedicine as example. So the most very classic from biomedicine is this different patient blood samples as different rows and columns at different genes, gene expression values. So you can have like G1 gene, G2 gene, many different genes, maybe in the human case, G20,000. And the samples, the number of patients are normally very much smaller than that 20,000 or 30,000. So in the normal scale, so we normally call this type of matrix as n times p. N means the number of samples, p means the number of features. In many biomedical tasks, p is super large and n is smaller. P, it's roughly, maybe in this genetic case, is about 20,000 or 30,000. N, it's roughly 100 or within hundreds. All right, so remember that. And if this is a text data, P is also normally pretty large language data, because English vocabulary itself, you normally have like millions, maybe make it a little smaller, hundreds of thousands of words. That's your P. But in the language data, your N is also super large, just thanks to the internet and World Wide Web, right? So different type of applications. So I did not put application as my variable, because I think that's a little bit outside the machine learning, but you have to kind of keep in mind data. So there are tabular data, but there's also different kinds of tabular data according to applications. So they may be all tabular data, but their properties vary according to the application type. All right, so this is our general view of how we look at our program. This is more like your first homework. And I already showed you in the previous example, right? You have X train part, Y train part, X test part, and Y test part. And then you just apply, you code that two modes to X train and Y train to get the F, and then apply the F on the X test, and then compare FX test and Y test, and that's it. Okay, I see the question. So if you need a multi-dimensional output, yes, you actually can have a multiple Y. So in this case, I just make it simpler. I make a scalar one-dimensional output. You indeed can have multi-dimensional output Y. All right, so now, other than the tabular data, in fact, in this classic AI, we are pretty dominating by the sequence data types. So what I meant sequence type, it can be language data, which we showed in this Amazon review text, or audio data, or sensing data, or protein sequence data, genomic sequence data. There are just many different kinds they are data located in this sequential linear dependency order. So this is what we call sequential data type. And there are many different than the tabular data. The output of a lot of the sequential data type are much more complicated. So let's use language as example. So we already tell, right? So in the previous page, we just predict maybe this specific person using gene expression, has he get COVID-19 or not? I'm just doing a pretend task, but that's actually feasible. It's fine. It's an okay definition task. But in the language task, in fact, its output is not just binary. In most cases, it's more like a tree structure because that's your parsing, right? Part of speech tree structure. It's just so complicated, really complicated. And this is the same case for genomic tagging too. So for those of you who maybe have genomic background, you actually know there are intron, extron, different function elements, different functional annotations. It's really complex. So it's not just a simple binary output anymore. And then another really interesting type is something called 2D grid data types, images. So for example, this case, we can have, like in this case, it's X-ray. In the this corner are the chest X-ray data. It's in fact a Kaggle competition. And then we also have the image net competition, which has like training data, 1.2 million images, and then the target labels is about 1,000. And there's also, so imaging data is just huge. There's this galaxy data, like it's just really, really large. And I think the recent, there's really the profound changes are pushing in the biomedicine domain using imaging-based diagnosis, imaging-based prediction. So it's really huge happening now. This is the second type, and then the third type, actually that's the third type. This is the first type, very popular and important, is the graph data type, especially the social network data. It was really used a lot in all those recommendation systems that maybe if you use Netflix or Amazon, how you're getting the recommendation is based on a lot of this graph data type of modeling. Those users have similar tastes. Those users maybe it's your friends, have similar profiles, and how to model this type of graph data is also a very big topic. And you can categorize the whole machine learning according to, are they tabular data? Are they just for sequential language data? Or are they just for imaging data? Or are they photograph data? So this is give you a very big categorization, and different venues, in fact, in computer science focus on different data types. All right, so we finished the data component. Now let's come to the task component. So in fact, the task, almost the majority of the machine learning literature or the education, most of the education or the courses, I mean, if you look at what most universities, the machine learning, how they arrange the lectures is according to the tasks. People normally just categorize or maybe chunk their lectures according to, okay, this is a chunk about supervised classification, this is a chunk of supervised regression, and then another chunk maybe unsupervised learning, which has been done by my previous years. But now, in fact, I'm starting to, this year I'm doing a different way. So you're going to get what I'm seeing now. I doing the bigger chunking according to data. I'm doing the smaller chunking according to the tasks. So this is more a hierarchical way now. Because more and more I feel only just segment the content according to task. It's not as practical as we're going to use, the sectioning we're going to use. All right, so supervised classification, it's very, very simple. It's just that Y, this target Y is just a discrete. If your target Y is discrete, you're performing a supervised classification. And supervised regression, if your target Y is a numerical, and then you want to predict that numerical values as close as you can, then your task is a supervised regression task. And there's also cases you don't have a Y. So this is also very classic. It's called unsupervised learning. There's this figure actually show you something called clustering. And it was used very predominantly actually in many more science related data, for example, single cell data. The hierarchical clustering is also very, very popular or dominating method in the biomedical data analysis. All right, so this is why you have no Y. You still want to group the examples. And this is a classic task called clustering. And then echo what I just mentioned in the sequential data output or the image data output. So your output, not necessarily just one scalar. So your output is a scalar, it can be a scalar in this, maybe for example, in the second row. So this is the image. So let's look at this column. The last column has image input, right? This is, I call that two-dimensional grid. And what I'm trying to predict is to classify each pixel on the images into a type. So for example, in this figure is some parts are sky, some parts are building, some parts are car, some parts are road. The prediction of a pixel, it's in fact highly dependent on the prediction of its surrounding neighbors. So when you're making predictions, you really need to consider its neighbor's prediction too. So this is what we call, so again, so I'm not predicting the whole image. My samples now, it's a pixel in this image. The output space is large because I need to classify every pixel in this image into a class. And I need to consider neighbors' Y output to consider what should be my output, right? A sky pixel is very much likely to be surrounded by sky pixel too. So you really need to consider this type of dependencies. And this is called structured output learning. There are many different kinds of this kind of dependency. It can be spatial. In this image case, it can be temporal, where you're working on sensing data. It can be also relational when you're working on graph data. All right. And then this really very popular now is something called reinforcement learning. So reinforcement learning is, we can even just, so the XY here. So I mean, assuming I'm using this policy style of prediction, so my current XT will predict a action T, and this will generate my next state XT plus 1. Then I'm using XT plus 1 to decide what should be the AT plus 1. So I'm saying that's action, right? Just to make it easy to corresponding to what we used here. Then you replace that into Y. Okay. So the whole formulation is an agent interact with environment, but you never know. You are never given an XT-YT pair to train the agent. So that's the classic RL setting. And what you only get is what's the reward when you're doing this XT-YT and you're projecting what's the reward, like maybe like the Q or maybe that's RT. That's specific. What's the reward I get at that specific state? And I actually do not know at the current XT, what YT should I take? But I know the reward, and I know the previous history of the reward. And I need to decide when I'm in this XT plus 1, what is the YT plus 1 action should I take? So which means I don't have XT, YT like a supervised setting, but I also not like unsupervised setting. I have some kind of reward function to tell me what are the better YT. But it's not a clear YT label given. So it's kind of in this middle of supervised learning and unsupervised learning. There's also dependency, sequential dependency among the samples. So this type of formulation makes it very interesting for decision-based agent, right? Because every agent, if you think about it, we're going to interact with the world, maybe interact with the user to making decisions. So this is a very important task formulation. All right, so let's wrap up for the second module. The most popular task is the supervised classification, which you already know, 2 modes. And you have X, Y pairs, and then this X question mark, and then Y is discrete. And for the supervised classification, there are also many different kinds. There's binary classification, multi-class classification, hierarchical classification, multilabel classification. There's also the structured classification, which I just roughly covered. So let's just, again, revisit it. So the binary classification is this classic first example ever we actually touched, the sentiment classification. Is this piece of text tell me a positive product review or a negative product review? Very easy. And it also has a lot of applications in biomedicine, which I just put it here, using gene expression of patient blood samples. Hopefully you can categorize those healthy versus disease type. Yeah. This is a very brutal definition. I think for those of you maybe going to love me if you have a lot of biomedicine background, but just it's roughly. I understand there's so many disease categorization, right? I mean, you have stages, you also want to predict stage. So it's not just a binary yes and no that you're interested. All right, so there's also multi-class classification. Multi-class classification almost is the first most popular and standard supervised classification problem like machine learning crowd worked on. And part of it because there's a very big, huge benchmark data and just very early on got available for people to perform text categorization. Another really popular multi-class classification is this 100 digits 0 to 9 classification. These two tasks are almost the most simple and earlier tasks machine learning researchers worked on. So just to make kind of analogy and comparison to this binary cases we had, in the multi-class case, you actually separate the space into like maybe like this A, B, and C. Oh, actually, it's not A, B, C, so this already give you. So for example, you have a text web from the web, you want to categorize it into a sports type or a science type or an art type. Yeah, so they don't overlap with each other, which in the multi-class case, I'm classifying a text, a sample, to only one class. So this is important. It will be only in one of the class. This is called multi-class classification. And then there's something called hierarchical classification, which actually being used almost the first important application like Google and Yahoo actually implemented, used this machine learning driven models like Google News, right? Google just categorized all the webs on the internet into this hierarchical labels that they handcrafted. So in this case, the hierarchy is this world, US, business and technology. And inside technology, you have iPhone, Microsoft, Minecraft, all like this lower levels. So your classification is to make a ladder, a series of decisions almost. So the higher level and the lower level, there's some kind of hierarchical label space, have even like deeper, not just 2 levels. And this is a very important standard task. All right, so one more, something called multi-label classification. So for this image, you can predict it has a castle, it has mountain, it doesn't have car, it has road. This is different from multi-class classification. So we already mentioned, right? Multi-class classification, you only classify the sample into one of the labels in that multi-class set. But here, you will have maybe multiple labels for this image. This is called multi-label classification. And actually, it's not just classification. There's also some recent very interesting task. It's generalization task. So our task, it's not just X to Y, right? Everything I just told you is X to Y to learn F function. But there are some recent tasks. I think this can be, yeah, this actually still fit there, but yeah, yes, sure. So this one, you're having the edges, you're generating images, but this Y, it's very, very vast possibilities, right? So let's see. So the ground truth is like this, but you actually can generate as long as this edges fits. And they're all different kinds of texture, all different kinds of colors, different kind of styles. And it's just not a Y anymore. It's a very interesting, we can actually flip this. So it's some kind of conditions on some kind of Z, and we're generating X. We're generating samples. And very versatile, different kinds of samples. This is called a generation task. And then you can also across modality, right? You can use text to generate images. You can also use a query to generate maybe some, you can use a summary to generate an article. So this new category is really interesting, and it's actually it's a very, very good task.